Okay, so what I would like to talk to you about is RabbitMQ and in particular the request response pattern. So let's start with the very basic question: why do we have specialists? Now, as you all know, this is a trivial question. We all do know the answer. But let's think about it. So why can't we learn everything? What is the problem, the main problem? The main problem is that human capabilities are limited. We just don't have enough memory and some other stuff possibly. So we have to specialize in different stuff. To become masters in one stuff, we should focus on it. So we have policemen, sellers, cleaners, and other people. We have a very complex human network. We exchange information between each other. We achieve goals by communicating, by specializing, etc. So let's talk about a few advantages and disadvantages of this model. So specialization is better local performance. What I mean by that is if we focus on one thing, we can master it. Also, less resources are wasted. We are human. We can't really learn everything. So what is the point of wasting our time and effort to learn? We are developers here. There's no point in wasting our time to learn, I don't know, cooking. Or maybe there is, but there are other people that can cook for us, right? We just make money. So what are disadvantages? Well, one of them is that it's sometimes difficult to reach a particular specialist. So, for example, let's say that I want to buy a car and my car dealer lives somewhere far, far away. So I have to get to that place. I would take a train. So then I need someone who will operate that train. We need other specialists. We need some intermediate steps to achieve our goals. If we were to know everything, buying a car would be very simple. I would just walk out of my house and go straight to my neighbor and, yeah, give me a car. So how does that apply to programming? I'll be talking in the context of web servers and web applications. So let's have a look at the classic web server architecture. As you can see, it is very easy to understand. We have a request which comes from the internet. It goes straight to the web server. The web server processes it. Perhaps it calls ADB. And then when it finishes processing it, it responds back to the internet. Notice that on this diagram, if the traffic goes high, then we add new web server instances, new nodes. Each one of those nodes in the classical architecture is the same, it's just a copy. And we put a load balancer in front of it, and it does the job. So, the advantages and disadvantages of this approach. As I said, it does the job. We did it, we do it, we will do it. It's well understood. And it works well, it's efficient. At least if done well. So it's well understood, so also there are lots of experienced people out there who can help us, developers. We can hire them. But there are also disadvantages. First disadvantage is it does not scale out of the box. So we have to write or do some custom things. We have to add the load balancer, we have to configure it. We have to write some code that will work in this more concurrent environment. And there is no isolation. Each web server, from the code point of view, it's a big blob of code. And we don't isolate these codes. In each node, everything is the same. So the code becomes bigger and bigger, more complex and messy. It's easier to write bad code. So let's talk about a different approach. RabbitMQ. What is RabbitMQ? So RabbitMQ is an open source message broker. It's a fancy name for a messaging system. It's a web server, not web server, a server, and that processes messages. Messages go to the RabbitMQ and from one server, and the other server can take messages back. Some characteristics. It supports advanced message queuing protocol, which is one of the standards in messaging nowadays. It's very efficient in terms of each node can process messages very fast, but also it scales well, it supports clustering. Everything is built in. And some numbers. Google and Pivotal achieved 1 million messages per second, processing of 1 million messages per second. So to show you how big the number is, if you consider United States, 2012, there were 6 billion text messages processed a day. 1 million messages per second, it's 86 billion messages per day. So it is more than 10 times United States texted. RabbitMQ is fault tolerant. It supports both durability and replication. Of course, with this durability especially, it comes trade-off. The performance gets worse because, of course, if you use durability, when you have to save some data onto a disk, it's not as fast as processing in memory. And with RabbitMQ, it is very easy to monitor performance, and I will talk about this a bit later. So that's how it looks. We have a couple of servers, the blue ones, and the red one is a RabbitMQ server. The servers don't communicate with each other directly. Every communication goes through RabbitMQ. So let's talk about how internally RabbitMQ works a little bit. There are a couple of entities that are used, names, conventions. So we have producers, exchanges, queues, and consumers. Producers just produce messages and they pass it to exchanges. Exchanges do something with those messages. A couple of things. They can publish them into, generally they pass it into queues, but they can do this in many ways. For example, in the diagram here, this exchange takes a message produced by a producer and then it copies it into two different queues. And there are consumers which take messages from queues and they process it. Note that producers always pass messages to exchanges, while consumers always take messages from queues. RabbitMQ supports routing, so not all messages have to be passed down the arrow. There is something called routing key. With each message can be tagged. So for example, in this diagram, we have messages tagged as big trans and normal trans. And whenever there is a message with this tag, it will go to one of the queues, but not to both. Consumers can be producers as well. There's no problem. We can just publish another message from a consumer once it finishes consuming the stuff. So as you can see, we can get this whole diagrams quite complicated, perhaps too complicated. And we end up with a very strange architecture. This is the architectural mistake. As you can see, there's a cycle here. The exchange passes message to another one, and back to the initial one. So this is bad. This is bad because obviously this message will travel infinitely times. It will never end. It will eat resources, and eventually it will kill our server. But fortunately for us, RabbitMQ knows how to handle this, and it will warn us about it. It will not allow such cycles. So the consumers are specialists I was talking about at the beginning. These are, programmer can focus on writing one simple thing, and he won't be distracted with the other stuff, specializing is a good thing. How we use RabbitMQ at Web Interpret. So what do we do? First of all, we help people to sell their products. If they want to go international, they can go to us and we will list their products on different eBay sites. That's one thing that we can do for them. And in order to achieve that, obviously, they won't translate the same product to different sites. There would be no point for us. What would we do, right? So we translate for them so they can easily just list them and don't worry about anything. So how does the process look like? We start with the client. He wants to list an item, let's say on eBay or Amazon or whatever. We copy that item for each site he wants to list onto. And then each copy goes to RabbitMQ for example, for translation. There are other things that we handle, other things that we process. Let's focus on this one. Then once those items are processed, which means translated in this context, they go to another queue, queue for items scheduled for listing. And there's one more worker that whenever there's an item in this final queue, he just lists it on the eBay site. And this whole process is asynchronous in the sense that none of the steps wait for any other, just goes straight. So we've encountered many issues with RabbitMQ. So the technology is not ideal, like there is no ideal things. The first one is that it is difficult to debug and trace messages. Obviously, if we have this very complex graph of queues and producers and consumers, then we can get easily lost. Error handling is painful, very painful. What we do at Web Interpret is that each worker uses two queues, one for messages that it should process, and the other one for failed messages. It works, but it's not perfect. Workers are separate processes. So we have to monitor them. If they die, this is bad. We have to resurrect them. RabbitMQ does not support priorities. So we can't really tell it, hey, that message should be processed before others. It's more important. We can't really do that. It can be somewhat simulated by multiple queues, but it's more of a hack, not really a feature. So the request response pattern, also known as RPC, remote procedural call pattern. Before we go straight to the code, let's have a look at the web server architecture. It will be a bit different than it was before. Now, when the request comes, it goes to the web server, and the web server does not process it. It just passes it to RabbitMQ, and then workers take care of everything. When they stop processing, when they finish processing, the response comes back to the RabbitMQ, back to the web server, and finally back to the internet. So the web server is not really a web server anymore. It's more of a proxy. But there are still things that the web server should do, like, for example, the request validation, the URL checking, perhaps authentication, and other simple stuff that occur on every request. But every heavy request, heavy resource consuming request should be passed to RabbitMQ. And this is the pattern. So let's focus on it for a moment. The web server issues a request to the RabbitMQ. Request is just a message here. And this message should contain two important information, one of which is the reply to queue, and the other one is the ID of the request. It goes to the worker queue. The worker queue gets the message, processes it, puts the response into the my queue. The my queue is taken from the request, metadata. And the web server takes the message from my queue, and based on the ID, it matches the response with the request. So, as you can see, the worker queue is associated with the worker, while my queue is associated with the web server. Both of them are producers and consumers at the same time. This pattern fits perfectly with asynchronous programming. So as you can see, whenever I issue a request, I could attach a callback to that request, and when it comes back, I can fire that callback and push the data to the internet. But what I'm going to show you is not an asynchronous approach, but rather a synchronous approach. So let's talk about Python. Before I show you the implementation, let's focus for a moment on libraries for RabbitMQ. The first one, and the officially supported one, is Pika. The one we use, at WebInterpret is Kombu. We use Kombu instead of Pika because that's how it was designed. But the reason is that although Pika is officially supported, it is kind of buggy and it lacks some features that we needed. Celery supports RabbitMQ. And there are other libraries like PyAMQlib, Puka, etc. I don't know much about those libraries. I just know that they are there. Code. Now, we start with request, so the beginning of the upper part of the diagram I've showed you. This is quite simple. We store events in the global events dictionary. And I am using here event objects from threading library. The application connects to the RabbitMQ, to the worker queue. We generate ID, we put the event object into the events dictionary. We send our message, and here we wait for the response. It's going to be processed in a separate thread. This is a threaded version. And once the separate thread gets the response, it will tell this thread to wake up, to do the stuff. The worker. Again, not really complicated. It listens on the worker queue, gets the message from the queue. The message object has ACK method. It's for acknowledgement. It's an internal RabbitMQ mechanism to acknowledge messages, to tell it, yeah, I've received this message, everything is fine. We take the payload, the data that is stored there, the data we've sent, and we do something with the data. Once we get our result, we connect to the reply queue and put it in there. Of course, this is a very simplified version. There is no exception checking and some other stuff, no cleaning. It's just to show you how it can be done. Of course, it's not for production use. And the response thread, again, quite simple. What we do here is we reuse the same events dictionary I've talked about before. Get a message from my queue. We acknowledge it, and then we match the response with the request inside, by this events dictionary. Once we find the event object, we just wake it and tell the other thread to continue the job. This is how it is done. Of course, the code is very simplified. It's not ready for production use. There are many things that has to be done. Proper error handling for both sides. We should avoid memory leaks. The events dictionary can leak memory if something goes wrong. Cleaning of, let's say, timeouts and cleaning the timeouts data. Perhaps ratioing tasks if needed. The code there used the simple queue, which is very simplified combo version of producer and consumer objects, which is not quite efficient. We could cache connections, so to improve performance. We could properly configure the RabbitMQ itself and tweak it for performance. That should be done. So let's have a look at benchmarks. Now, I've written here that they apparently matter. What I mean by that is, obviously, if you want to use any of that stuff, you have to do your own benchmarks. It's not suited for all possible cases. The setup. I've tested it on my local machine, 4 cores with local RabbitMQ. I've used 2 workers, one short worker which sleeps for 70 milliseconds and one long worker which sleeps for 210 milliseconds. This is to emulate, let's say, long-running queries versus short-running queries on the DB. I've tested the classical version versus the RabbitMQ version, and the RabbitMQ version had 4 threads, 4 workers. 3 threads were used for the long worker and 1 thread for short worker. I've used UWSGI web servers, 1 process, 4 threads. And the implementation is that the web server randomly takes one of the workers and passes a message to it. And these workers are taken with 75% probability for short worker. So short worker occurs more often. And I've used A/B test. So let's have a look at numbers. Concurrency level 4 for request parallel. Remember that I have 4 cores CPU. So for the classical web server, the average time spent on the request is 212 milliseconds. That's as expected, since the long-running worker takes 210 milliseconds to complete. RabbitMQ without durability. This is 342 milliseconds on average. So as you can see, it is around 50%. It took it around 50% more time to complete. Obviously, this can be taken down, the difference, simply by using multiple servers, because all of that stuff happened on my one local machine. The web server, the RabbitMQ, and workers. So it's an possibly unnecessary overhead. And the RabbitMQ with durability, the average response time is 378 milliseconds, which is a little bit more, but not really a big deal. Let's have a look at concurrency level 16. Classical web server, 842 milliseconds on average. So it is 4 times more than in previous benchmark. This is again as expected. RabbitMQ without durability, 1150 over a second. Again, this is 4 times more than in previous benchmark. It is good, still as expected. And RabbitMQ with durability, again 4 times more. We've increased concurrency 4 times, times increased 4 times. It's good, it's not bad, it scales well. Okay. So, what can we use it for? Let's start with what we should not use it for. General request handling. We don't want to send every possible request to the RabbitMQ and for some worker to handle it. It's a huge overhead, unnecessary. Authentication. Again, we check for a user, for an authenticated user on each request. We don't have to do this via RabbitMQ. Serving static files. Again, this would be horrible. This can end very bad because RabbitMQ can't really handle too big messages. If you were to put a huge file like 100 megabytes into RabbitMQ, it will just break. But what we can use it for? AV task handling. So if our web server has to do some hard processing, we can just pass this request to our workers. And if we need more horsepower, we just add workers. Not a big deal. We can do this on the fly. We don't have to stop the production server or do any magic. Very easy. And to integrate similar yet distinct and complex systems. For example, at WebInterpret, we integrate eBay, Amazon, and we do translations. So these are all different components, but they share some stuff. So they communicate. We communicate via RabbitMQ. Right. Monitoring. I've said it is very easy to monitor performance. So let's have a look. RabbitMQ is shipped with the admin interface. As you can see, there are lots of stats here. And so let's say that I am running this long worker and I want to check the performance. Do I need to add workers or perhaps remove? So I just look at those numbers. I see that this queue is empty. This queue is empty means that all workers do their jobs. But there are at least, we have, perhaps the number of workers is too high. So to check if the number of workers is too high, we can look at message rates. If these are very low, the ACK, for example, then it means that we have not enough workers. But if the ACK and delivery and incoming message rates are pretty much the same, it means that they do all well. Perhaps we can remove some workers. We waste resources, we waste servers. So monitoring is easy. And vice versa. If we were to see numbers in messages, then yeah, we have more messages than we can process. We need more workers, we need more servers. Adding a worker is very simple. You just run a worker, he will communicate with RabbitMQ. Right. So, to summarize things, what are the advantages and disadvantages? The first one is that we have good code isolation. We don't have to worry about, we can focus on one thing and master it. We are not distracted by some other stuff, perhaps legacy code. It's easy to scale. As I said, if we need more horsepower, we just add worker. We don't need to worry about configurations, about load balancing. RabbitMQ takes care of everything. And it is very easy to monitor. The performance tuning can be done. The disadvantage is the worse performance. As I said, the 50% more overhead. It's not something that should be ignored. Okay, that's pretty much it. Have any questions?
Okay, you said that your example server lacks reliability and so on, all these missing features. Have you any design fleshed out for it? Do you know, for example, have you got recipes for handling crashed workers, crashed servers, network partitions, and other problems? Because that is an issue with RabbitMQ eventually. So have you got a solution for that?
It's a good question. Well, there are not really, maybe What we do is just we monitor performance using some scripts. Like we monitor workers, so we ensure that they are always running. That's the first thing, and then the error handling is quite messy with RabbitMQ. Most of the time, you have to look at it manually, and for example, at the admin interface, and just see that like some queues are just the numbers are rising, nothing's going down, so something's wrong. There's lots of manual tracking at the moment, at least what we do at Web Interpret.
Thanks.
Are there any more questions?
So again, about debugging the issues with RabbitMQ. So the question is, you said that it may happen that some of the queues will have plenty of messages, and we know that some of these messages probably are the ones which are not valid currently. Yes, so some of the requests has been sent, some of these requests actually are no longer valid. So have you used in your experimentation or maybe production the mechanisms of timeouting the messages? Have you some experience? Can you share some experience with it?
Yeah, well, we are not using any timeouts at Web Interpret. It's just once the queue gets too big, we manually clean it, and that's it. Normally, we don't have lots of issues with this. The error queues are hardly ever going too big, and we just don't need to clean them automatically or implement any sophisticated mechanism.
So one more question regarding using the durable queues. So are you using it on your regular daily basis, or because I know that
Yes.
there are some issues when the number of messages, number of queues is growing on performance of the storage. Yes, backend storage for this.
Yes, we use only durable queues. We don't use other. We use clusters of RabbitMQ, so the distribution is okay. It works fine.
Okay, thank you.
Okay, hi Roman. You told about that you can use, well, everyone can use RabbitMQ for RPC messaging. I think it's also worth mentioning that using message queue stuff like RabbitMQ, Qpid, or some other MQP servers is not sometimes also a good idea, because sometimes message queues, the queues is not required for that. So there is like
Yes, of course.
there are some similar approach, several similar technologies like ZeroMQ, which provides you nice opportunity for do RPC stuff without actually handling all those queues, without being able to replicate all the stuff, monitor all the stuff, and have all other problems related to that. So
Yes.
I mentioned ZeroMQ is also a good point. That's a good stuff at this point. Right.
Yes, ZeroMQ is okay if you are doing not really complicated things, but once your system becomes very big and complex, it's just handling it becomes nightmare. At least from my experience. Yeah, of course.
Any more questions? Okay, so thank you.
Thank you.